The first derivative can be used to study the behavior of a function. We can determine whether or not a function is increasing or decreasing based on the value of its derivative. However, that may not tell you much about the curvature of the function. So let's look at two functions. The first one in this black line is the function x squared. So what we notice is that the function is increasing. So the function is increasing from 0 to infinity. And what we notice about the slope of the tangent line is that the slope of the tangent line starts off at 0 and slowly inches its way up. So it is continuing to rise. In fact, the slope of the tangent line is moving towards infinity. So we find that the slope is increasing. So f prime is increasing. However, when we look at the function sine of x on the interval from 0 to 2 pi, or pi over 2, we notice that the function is increasing. So similarly, the function is increasing. But what we notice about the derivative here is that it is slowly planing off. It's slowly moving toward 0. So since the slope of the function is moving towards 0, what we find is that the slope is decreasing. So in this case, the slope of the tangent line is increasing, the slope of the tangent line here is decreasing. And so this brings out this idea of concavity or curvature. So if it's curved upward or concave up, then that is when when it's concave up, this has a relationship with the second derivative. This is what's called concave down. Now, you might think that there's concave and convex because in optics, that's how we refer to lenses, as concave and convex. However, in mathematics, convex typically has a different term, or is a term for a different concept. So a lot of times we just simply use the term concave up or concave down. So the way we determine this is we say, okay, well, f prime is increasing. Well, we know that when a function is increasing, its derivative is positive, or there's a relationship there. It's not always that. But when the derivative is positive, the function's increasing. So if the first derivative is increasing, it means that the second derivative is positive. So what we find is if the second derivative is positive, then the function is concave up because it means the first derivative is increasing. Similarly, if the second derivative is negative, that means that the first derivative is decreasing. So that tells me that it's concave down. So we now have a way to use the second derivative to give us information about the function. So we can kind of see that here by drawing tangent lines, but let's actually do the work and see if we can't prove that result. So if I know my first derivative of x squared is just 2x, and my second derivative is 2. Well, that's actually always positive, which tells me that no matter what, for this graph, it's opening upward. The curvature is opening upward. So that's what this is telling me here. Now, what about this function? Well, if I take the derivative of the sine function, I get cosine. If I take its second derivative, I get negative sine of x. So what that tells me is that the concavity of the sine function is directly related with the actual value of the function. If the function is positive, it's concave down. If the function is negative, it's concave up for the sine function. See, if we were to continue to draw this, we see that the function is concave up here, but as soon as the function becomes negative, it's concave down here. As soon as the function becomes negative, it becomes concave up. So the sine and cosine functions have that kind of interesting behavior that way, that their derivatives, their concavity is the opposite of the function value. or at least the second derivative's value is the opposite of the function's value. And you could apply this to any number of functions, and we're going to do that for some more explicit functions coming up.